Hi, I am Mina. I am an AI engineer at the Research and Development Division at Intexel. Also, I am a master's student at Arizona State University, majoring in computer science. And today I am presenting left ventricle segmentation using scale-independent multi-gate unit in MRI images. So, cardiovascular disease is a term that's used with the diseases that affect either the heart or blood vessels. And actually, it's the number one cause of this globally. It kills more people than any other disease, and actually common in high-income countries and uh, low countries and middle income countries as well. However, in low and middle income countries, people have another issue is that they do not have the benefit of integrated primary health care programs to help diagnose and treat these diseases. Moreover, the ratio of the number of doctors to patient in these countries is quite small. So basically, it takes much longer for a patient to get his scan analyzed and diagnosed. Left ventricle segmentation is an essential tool that helps with the diagnosis and risk assessment for the myocardium. It actually provides some key measurements like ejection fraction ratios that can be used for diagnosis later. And actually, to get this segmentation, radiologists or operator needs to manually annotate the boundaries of the myocardial muscle itself. And actually, this is a very very time-consuming task because the operator has to sit down in front of many images per case and go through all of them to select just a very small subset and then start drawing on them by his mouse with connecting these green dots. So it's a very time-consuming task. Also, it has another issue is that it's not reproducible. Results can change between one radiologist and another, and even the same scan passed to the same radiologist. So there's issues with result reproducibility, and there is also always the operator bias present in the assessment and annotation. So, number of approaches have been suggested to address this issue, and broadly they can be classified into two categories. Methods that use classical computer vision, classical approaches that use image processing techniques to solve the issue, and methods that are based on deep learning approaches. For the classical approaches, one of the early approaches was multi-level thresholding. And basically, the idea, given a grayscale image with multiple classes in this image, with multi-level thresholding, it tries to maximize the variance with intra-class variability, the variability between classes. However, this approach fails when the area of the object of interest compared to the background area small. And this is actually what happens with MRI images. They have usually a large field of view, especially for small slices like the apical slice. The area of the heart compared to the overall area of the image is quite small. Some other approaches related to the deformable models, level sets, graph cuts, active shape models. The issue with the model-based approaches is that they have limited capacity to generalize beyond the training set. I mean the automated methods of model-based approaches lack the robustness when tested on cases outside the training data. So regarding the deep learning approaches, many approaches have been proposed. However, one of the most performing nowadays is the models that use encoder-decoder-like architectures. UNET is one of these architectures, and it is one of the most successful architectures for segmentation of medical images. However, in some studies, it has been shown that it lacks the ability to properly segment the apical slices from the image. It cannot handle the change in size variability between basal and apical very well. So here we propose an enhancement to the UNET to increase its ability to become robust against these changes in size of the heart, as well as it will enable the architecture to better use the image context and overall yield better segmentation. Here we have edited the encoding path of the UNET, the contracting path. We have proposed the multi-gate block, which consists of two components: the Inception block, the orange one, and the average pooling The Inception block serves as a multi-scale feature collector, as will be discussed in the later slices, and average pooling has the ability to aggregate context of the image at different levels of the network. Also, it's worth mentioning here that this green block, we call it the standard block. It's just two 3x3 convolutions followed by each other, each one followed by a batch normalization and low activation. So for the multi-scale Inception block, it uses actually dilated convolution. Dilated convolution is a special type of convolution where we introduce like holes between the kernel values. For instance, on the left, this is a 3x3 kernel with dilation rate of 1, but on the right, it's same 3x3 kernel, but with dilation rate of 2. And the advantage or the benefit of using dilated convolution is it can actually increase the receptive field of view without actually increasing the number of parameters of the network. So it's efficient in this regard. So the Inception block we have is consistent of 4 parallel kernels with different kernel size and different dilation rates. As the kernel size increase or dilation rate increase, we reduce a number of features, and these the output of these parallel convolutions are concatenated and then pass to a one-by-one convolution to merge these features and reduce the resulting number of maps to make the overall architecture still efficient and small in size. And the purpose of the Inception block is to enable the network to get the feature of the object of interest with multiple scales, to enable the network to detect the feature even if the object of interest size changes between one image and another. The second component is the average pooling. We apply the average pooling at each level of the encoding path. We have the input, and we at each level of the encoding path, we pass the input to the average pooling, and as you go deeper with the encoding path, the window size would actually increase. For instance, here we have an average pooling of whose window size is 2 by 2. Here would be 4 by 4 and 8 by 8 and so on if the network goes deeper. And actually, the intuition behind the average pooling is that as you increase the window size of the pooling, you make the image blurrier and it has less details. So it makes sense that this would actually make an abstraction for the details and make the network focus only on the context of the image at this scale. So yeah, the larger the window size, the blurrier the output of the pooling. So the more the network would pay attention to the overall picture and just not the details of each component in the picture. So to evaluate our architecture, we have used two data sets. The first one is LVSC, Left Ventricle Segmentation Challenge, that was released in 2011. It consisted of 100 annotated cases. It included both long axis and short axis view of the left ventricle. And to train our model, we split this data into the split ratio of 60 to 20 to 20% for training, validation, and testing respectively. The second data set is ACDC, Automatic Cardiac Disease Automatic Cardiac Diagnosis Challenge, which consists of 150 scans. It included the left ventricle short axis views only. And for the ACDC, it was actually split by the challenge itself into 100 patients with annotations. It's provided to us to use for training, and 50 other patients kept for testing. So results of LVSC, we have shown that the proposed architecture actually able to outperform the UNET in terms of DICE index by 1%. And it was actually able to segment both short axis and long axis view well. Even in some cases, the provided annotation, here's the provided annotation, or the ground truth is the green one, was a bit suboptimal. It was not the correct. However, the model was able to generalize better and get better contours than the ones that's provided. Even here the green contour is obviously off. For ACDC, here we do not only present the DICE scores, but also we present some clinical measures provided by the challenge platform. Some of the measurements are ES in systole blood ball DICE, in diastole blood ball DICE, in systole myocardium DICE, in diastole myocardium DICE, in diastole volume correlation, volume bias, and ED mass correlation and ED mass bias. As compared to the winners of the challenge, it's actually, we can see that the proposed method is very comparable in results. It actually outperforms the first winners of the challenge in ED bias and ED mass correlation and ED mass bias. Also in the three dias of the blood pool. However, it's worth mentioning that the proposed method is much smaller in size than the first winner of the challenge, as will be discussed later, and it's much faster. Here are some samples from the ACDC dataset As you can see, that there are some good cases and some failures, like here and here. So the whole idea of the architecture is to make it robust to scale changes, and also to make it use the context of the image better. So in order to test this idea, we have set up this experiment where we downsize the input image to 56% of the original size. The original size of the input of the network was 256 by 256. So we downsampled the input images to 192 by 192, and also down the input image to 25% of the original size, in order and re-evaluate the same dice score to see how the model performs when the image size reduced with this much. And to give a visual illustration of what's happening here, this is the original input to the network. Should take this image and get out this segmentation. This is the top row is what's going to happen with the image, and the bottom row is the output of our network. So this is the normal case, the first column. The second one is we take the inputs and just compress it to 192 by 192 and pad the remaining pixels with zeros to reach the original network size, which is 256 by 256. And again, do the same experiment with taking the input and downsizing it to 1/4 of its original size, which is 128 by 128, and re-evaluate the same measurements again. And as a result of this, the proposed method, the proposed versus the UNET on the image downsize, it actually, the dice only degraded by 0.5%. So this huge downsize of the image almost did not affect the proposed method. For the 128 by 128 image size, the proposed method dice degraded by 7.5%. However, for the UNET, it actually failed to segment the images. Most of the images were actually black prediction, did not actually find the heart within the image at all. So here we consider as failed. So in conclusion, in this paper we introduced another component to the native UNET, which is the multi-gate block. Here we believe this introduction or this block enhances the overall accuracy of the model and enables the model to better handle scale variability with images, especially for helical slices. The proposed method outperforms the UNET in terms of dice scores and other clinical measurements. The network again is robust against small objects like apical slices, and it was able to compensate the modest quality of annotation as seen in the LVSC results, where the ground truth annotation was actually not that accurate, but the model was able to correctly predict the boundary of the left ventricle. The model is very, very fast. It's very lightweight. It actually takes 0.0035 seconds per image when tested on an NVIDIA GPU, 1080 Titan X GPU. However, one of the shortcomings of the model is in this case. In this case, it detected 2 hearts instead of 1 heart. However, this issue we believe it appears because of the introduction of the multi-gate block. And the intuition is that with average pooling, you take the image and pass it to the subsequent levels of the input, but with blurrier version using the average pooling. So at this point, the model may be confused between these two areas because at high level they really look like the heart. And to solve this issue, actually, to solve it using the post-processing is just easy. It can be handled during the post-processing of the model output. And thank you.